A knife is not a Beyblade. You shouldn't be able to let it rip. So let's talk about warp. Warp is any bending or twisting of a part out of its intended shape. In the case of a knife blank, our intention is for the part to be perfectly flat and parallel on both sides. Now we can clearly see by resting this steel blank, which is made of CPM MagnaCut steel, by the way. It's a steel that's very prone to warping during heat treat. We can see by placing this blank on a flat granite surface plate, it rocks. Now if I flip it over, it rocks in a different direction. So these are two different types of warp, and these are both extreme examples of warp, which is why I'm using this blank for this video. First, we have a U-shaped bend warp. So that's a U-shaped bend, and that's what allows the blank to spin like so along this point where we have this Sharpie line. The other thing, if we flip it over, is you can see that it sort of rocks unevenly, and that's from a twist. So we have both a U-shaped bend and a twist on this particular knife blank. Now there's lots of videos out there that talk about how to avoid warp, what warp is, what causes warp, and that's not the focus of this video. In this video, I'm just going to show you how to fix warp once it has already happened. I may make a video in the future about how to prevent warp and how to avoid it and all that and what the causes are. But again, that's not the focus of this video. The point of this video is just you heat treated your knife blank, it warped, what do you do about it? Step 1, temper bending. Temper bending is a term I made up that refers to the process of bending a blank at or below tempering temperature in order to alleviate warp. Now, it's a fairly simple process. There is a little bit of risk involved, which I'll get into, but basically what we do is we use a jig that looks something like this in order to bend our blank in the opposite direction of the warp, which will alleviate some of the stress of the warp and straighten our blade. Now, let me briefly explain what some other people do and why I don't do it that way. The first way some people do it is they'll just take a straight piece of metal, they'll take their blade, and they'll put it so that the warp is facing down. In other words, they'll have it like this, where if you shine a light, you'd be able to see the gap between the blank and the metal bar. And then they just clamp everything down and then put it in the oven at tempering temperature and wait an hour or so. And when they take it out, hopefully it's straight. Now that works for very slight warps, and especially it works on non-stainless steels, but stainless steels are much more resistant to that sort of straightening when it's not done, let's say more extremely. And so this sort of method, while very uninvasive and very not risky, it's a very safe way to do it. It usually doesn't work for stainless steels or for extreme warps. Now in this case, I just showed you a blank that is both stainless steel because it's MagnaCut and has very extreme warp. So we're going to take a more drastic measures. Now another way that people will do this is they will place brass pins and they will bend the blade over that brass pin. And that is the optimal way to do it. But one of the reasons why I don't like doing it that way is it's much more finicky. It's a little bit more annoying to set up. And honestly, given that this is only the first step of the process and we're just trying to eliminate the majority of the warp, it really isn't necessary. And so what I advise is something that most people will actually do, which is be able to do easily, is just get two relatively straight bars of steel, have one hanging underneath the other. So we're creating this ledge right here. And you want this ledge, the top piece of steel, to be at least 1/4 of an inch or thicker. In this case, it's probably around like, 1/4 of an inch or something or more thick. And what we're going to do is we are going to set the blank on this jig, hanging over the ledge, approximately where the warp is. And if the warp is like this, right, then we will bend it in the opposite direction to counteract that warp. So I'm going to line up the ledge roughly with the Sharpie mark. We don't need to be super precise here. Like I said, step 1 is not a precision process. And I'm going to clamp it at the butt. I'm going to clamp it again at the ledge. And one important thing I want to mention is that if you want to be really safe with this part, because like I said, this is an extreme process to some extent, I would put this in the oven as is right now, get it heated up to around tempering temperature, and then do what I'm about to do, which is bend it. So we're going to bend it with this third C-clamp by bending it over this ledge right here. So I'm going to put the C-clamp out around the tip area. You can see as I tighten this C-clamp, we are bending the blade in the opposite direction of the warp. Now, don't go too crazy with this. This is about the most I would go for a very extreme warp. If you go too extreme and you do it when it's cold, you risk snapping the blade, which I have obviously done before. Here's an example of a blade that I have snapped because I went overboard and I didn't take the extra step of doing the bending after heating this up to tempering temperature. Now, in this case, for demonstration purposes, and because I've done this a bunch of times, I know how much I can get away with. But I would generally advise leaving it in the oven for about 30 to 40 minutes first, and then, with gloves on because it's going to be hot, do the final clamping and then start doing the bending. So now that we have it set up in the jig, I'm going to take it over to my even heat oven, right? I have an even heat KO 22.5 model that I'll be showing you in a second. And I will just put this entire thing in the oven and leave it in there for at least an hour. I have found that the more severe a warp is, the more helpful it is to leave it in for at least an hour. If it's a very light warp, you can get away with like 30 to 40 minutes. But for a more severe warp like what we have here, you want to leave it in for at least an hour. You can leave it in for longer than an hour if you want to make sure that the warp really gets fixed. So we're at the oven. I have an even heat KO 22.5 like I mentioned, and we can see that it's currently at 295 degrees Fahrenheit. I do already have some blades in the oven right now. These are blades that have already been finished heat treating, and the reason why I have them in the oven is for efficiency, because like I said, you don't want to be cold bending the blank like I just did here. You want the blade to already be warmed up before you bend it, because that'll decrease the likelihood that it snaps. And so I have a bunch of blanks in there already. Once I straighten this one, I'll put the next one in the jig and, continue to straighten them. But essentially, I'm going to be throwing this whole jig in the oven, and I'll be leaving it in here for at least 1 hour. You can leave it in longer without any damage to the blade because, like I said, we're still at or below tempering temperature, so it won't have any negative effect on the blade. And one thing I want to mention is that when we pull the jig out of the oven, so what some people will do is that while the blade is clamped down or bent, they will put cold water over it to lock it in. This is very risky when you're doing extreme bending like what we're doing here, so you don't want to do that. That will greatly increase the risk of your blade snapping. What you want to do is once an hour or more has passed and you pull the jig out of the oven, you want to unscrew all the clamps, take your blade, and then rinse it in cold water. And that'll be a lot less risky, and you will still have your blade be much straighter than it was before going in the oven. So after temper bending, you can see that the blade is a lot less warped. You still have a little bit of rocking, but not nearly as much as before. And the twist even gets lessened a lot because twist is partially a product of the U-bend as well. It makes it a lot worse. You can see it isn't even rocking much at all in the same direction it was before. So now we're going to move on to step 2, which is carbide hammer peening. So let's move on to step 2, carbide hammer peening. So we're going to use this hammer, which is a modified hammer. We have a carbide ball, which is super hard, brazed into this hammer. And this carbide ball is much harder than the blade steel. The blade steel in this case is around 65 Rockwell. This carbide ball is much harder, and so we'll be able to create indents in the blade that stretch out the material and will help us get it perfectly flat. This is just step 2 of the process. This is also not a precise process. It is impossible to get a perfectly flat blade with just a carbide hammer. The reason why we did temper bending before this process, because if the blade is way too warped and you try to flatten it out completely with the carbide hammer, you would have to be hitting the blade pretty hard. And in so doing, you can actually crack your blade or even break it in half entirely. And so the safer way to do it is to do temper bending first in order to alleviate the large part of an extreme warp. And then for the last little bit, like we showed earlier, we're going to hammer it to get it out. Now, quick note, you're going to want to have the blade with the U shape pointing upward. So it's a U shape like this right now, not like this. So if you place it down like that, and we're going to, as we hammer it, let's say this is the U shape, it's going to slowly get flatter. So we're going to be hammering where the warp is primarily, right? Where you're basically hammering the valley of the warp, not the peak, if that makes sense. All right, let's go check how much that did. You just want to do a little bit at a time. I check it on a granite surface plate because that's about the amount of precision we want from this step. So I'm going to move over back to the granite surface plate. We'll see how much of a difference we made, and we'll go from there. You can see where we made indents with the carbide hammer, thereby peening the blade. And what you'll notice is that the blade is no longer rocking nearly as much as it was before. Also in the twist direction, right? Barely any movement. So we're going to call that good for this step of the process. Like I said, the temper bending and carbide hammer peening parts of the process are not precision processes. This is where we're just trying to eyeball it and get it as flat as possible by eye, by feel. What we're going to do next in step 3 is where we first start doing actual precision processes that involve surface finishing. So let me go ahead and grab a blank to show you an example of what we're going to be doing in step 3. Step 3, double disc grinding. So the vast majority of knife makers do not have a double disc grinding setup or machine, obviously. Most people will have the ability to outsource to a local, or you can ship it to a double disc grinding place and they can do it for you. It's typically not a super expensive process, and if you really value flatness in your parts, then it's a not indispensable part, but pretty darn important part. Now, the reason why double disc grinding is so nice is because you remove material from both sides of the blank at the same time, because what it involves is 2 discs, in other words, double discs, and you're abrading the surface of the blank from both sides with 2 abrasive discs. And that maintains the parallelism of the part, which is very important for folder blades, not as important for fixed blades. And so for a fixed blade, honestly, you can get away with a lot less flatness and a lot less parallelism. In fact, you don't even need any parallelism at all, to be honest, which is why some people will do these tapered tangs, which are obviously the opposite of parallel surfaces. And that's fine too, as long as the surfaces of the tapers are flat themselves for the scales to sit on. But if you do really want a flat part, you will want to send a double disc grinding, and that accomplishes 2 things. First, you get a decent finish. This is a double disc grind part. You get a decent finish. You can see the radius of the double disc grinding disc, that circular, these arches, right? And this part is really nice and reflective. The RA finish is, you can request a higher finish if you want. I get the lowest finish, and it's still pretty nice because I'm going to remove it anyway. But you get the part to be flat and parallel within 1/1000th of an inch, which is more than you need for a fixed blade, but I do it because I value flatness and parallelism. It gives me better results. It gives me more accurate readings when I Rockwell hardness test, so I know I'm giving the customer exactly what I'm promising. And so there's some reasons to do it. If you value precision and you value accuracy and you value honesty, there are some benefits to getting things perfectly flat and parallel. Now, one thing I will also say is that double disc grinding, you can just say, like I said, it's flat and parallel within 1,000. You could say good enough. Me personally, I want it to be flat and parallel within 2/10,000ths. So, about 5 times more accurate, more flat, more parallel. So what I will do is after double disc grinding, I will personally do a step 4 where I surface grind it manually. I have a stone surface grinder in my garage that I use to do that. And I'll show that process really quickly, what it looks like. But essentially, These are parts where, now after you do the carbide hammer peening, it's really up to you how flat you need your blades to be or how flat you want your blades to be. If you're aiming for truly flat and parallel parts, you will need to surface grind or double disc grind or both. But if you don't need a perfectly flat and parallel part, there are other ways to flatten your blades, which I will briefly discuss after I show the surface grinding setup. I won't waste your time explaining how a surface grinder works and why it creates the most flat and parallel parts possible. However, I will show you a few of the reasons why we did the earlier steps before getting to this step. So when we get to surface grinding, you have what's called a magnetic chuck. So this is there's actually a magnetic force applied here. And so when I put this part on, I can move it, right? When I turn this lever, that activates the magnetic force and I can no longer move the part. Now, the reason why this matters is because this can create the illusion of flatness where there is not actually flatness. Let me explain. So let's say that you have a U-shaped warp like this, right? Let's say that it's cupped upwards like this, right? When you activate the magnet, it's going to flatten the part because the magnetic force is pulling everything down. Now, if you then surface grind your part, right, you get it all nicely finished and it's all the same thickness throughout. When you undo the magnetic force, it's going to go from flat back to warping because that residual stress is still there. That's why you can't. That's one reason why you can't just instantly go to surface grinding on a warped part. You have to actually do, step 1, temper bending. Step 2, carbide hammer peening. Step 3, you can go from step 2 straight to step 4. You don't have to do double disc grinding. If you go from step 2 straight to step 4, you will get an equally flat and parallel part. So why do I advise double disc grinding specifically? A couple of reasons. One, surface grinding is very tedious and time consuming. Double disc grinding is very fast and not tedious, especially if you're outsourcing, obviously. The other benefit of double disc grinding is that you can remove a lot of material very quickly and still maintain that parallelism. And so if you have, for example, a blank like this that is much thicker than what I need, this actually comes 180 thousandths of an inch thick, and I want it to be around 130 thousandths of an inch thick. That's 50 thousandths of an inch of steel to remove. If you try to do that on a surface grinder, it would take ages, because the surface grinder, you want to remove maybe a few 10 thousandths here and there at a time. It would take forever to remove 50 thousandths of an inch. And so the reason why you would want to put step 3 in and do the double disc grind is primarily for efficiency. You would get a bunch of blades double disc ground at the same time. They would all be within a thousandth of an inch in their thickness and flatness deviation, and you would just be able to do that all in one go, and it'd be way faster. And that's part of the importance of the process, is that flattening blades is in itself a very inefficient process. You really save a lot of time if you use steels that aren't Magna Cut, that don't warp, which is, for example, K390, is a bowler steel that really doesn't warp at all. If there is any warp, you don't even have to do temper bending or carbide hammer peening. You can usually just surface grind it out because it's so minimal. I can take a heat-treated K390 blank, send it directly to double disc grind, and then just surface grind it, and it'll be a perfectly flat and parallel part, just to give you an example. But if you are working with steels like Magna Cut, because they're popular, because there's hype and demand for the product, then you will have to deal with some level of warp, which means you'll have to go through these steps of actually fixing that warp. And so those are the 4 steps. It's 1, temper bending for extreme U-bend style warps. Step 2, carbide hammer peening the remaining twist warp and remaining U-bend warp. Step 3, send it to double disc grinding. Step 4, do some surface grinding to get that final level of flatness and parallelism. And in bonus, step 5, if you have the access to it, would obviously be using a lapping machine to get a nicer surface finish. But that's not really necessary, and you will get a perfectly flat and parallel part off just the surface grinder in step 4. Now, you might have a question. Brian, why can't I just get a handheld magnet, stick it to my blade, and flatten it on the platen of my surface grinder? What's wrong with doing that? Well, there isn't really anything wrong with doing it that way. You will have a part that isn't as flat and isn't as parallel, but for something like a fixed blade, that can be good enough. The reason why this process creates a less flat and less parallel part is for a few reasons. The first reason is that often the surface you are grinding on itself is not perfectly flat. In this case, I have installed a ceramic glass platen, but let's say you're grinding with the backing of the steel platen, right? Well, your steel platen is going to dish over time. There's going to be gouges. It's not a perfectly flat surface. Even if you surface grind your steel platen, eventually it's going to develop more gouges and grooves and valleys. And so a steel surface platen is never truly flat. I would advise at least getting the ceramic glass platen. But even if the backing is perfectly flat, another problem is that your belt is not perfectly flat, right? Because your belt has give, right? It has cloth backing. So when you put this belt on, that's what you're actually grinding on. And so this belt has give. So that's one reason you're not going to get flat surfaces. The other reason is because as you are grinding on the belt, you are not perfectly applying pressure in all directions because you're a human being and it's physically impossible to do so. So some areas will get ground a little harder than others. You might apply more pressure here than you apply here or here. And so you're just not going to be maintaining that parallelism at the same time either. Another reason it's not as accurate is because this abrasive on the belt is not being equally used, right? The center part is grinding more material than the sides as you move your piece around. And so certain areas of the belt are going to wear away faster than others. And when they wear away, that means those sections are microscopically less thick or they're thinner than other sections, which means that you have a surface that is fundamentally spongy, not consistently flat, and you're not applying equal pressure all throughout. And so you will never have perfectly flat and parallel parts grinding your blanks on a belt grinder. You can get away with it on a fixed blade, but it really wouldn't be good enough on a folder. Next, let's talk about this. This is a surface grinder attachment for a belt grinder. And you might be thinking to yourself, well, it has the word surface grinder in the name. It must be just as good. Unfortunately, it isn't. It is a lot cheaper than getting an actual surface grinder sometimes. But really, like, the main problem with getting a surface grinder is usually not the cost. It's the space it takes up and stuff like that. The belt surface grinder attachments, I think these are around like $800 or $900. And my big surface grinder was only $1,500, so it's not that big of a difference in cost. Now, the reason why these are not as accurate as a stone surface grinder are legion. There's many reasons why they're not as good. Like I said, these are better than doing it by hand on a belt grinder, and they are good enough for fixed blades. But you really don't want to be doing folder parts on these because you're going to lose a lot of your flatness and parallelism. So let me explain some of the reasons why. So one of the main reasons, like I said, my main surface grinder machine is a large, heavy machine, and that's on purpose. You want a larger machine to reduce vibrations, which will lead to a more, it'll lead to a less accurate product if you have a lot of vibration, which these tend to have a lot of kickback and vibration because they're not heavy parts. They're not flimsy, but they're not heavy either. Another thing is that when you have this magnetic chuck that you are putting your blank on is you are truing it up with this wheel. Now, the problem with this wheel is there's two main problems with it. The first is that it's rubber and it's not as hard. And also, even if it was super hard, let's say it's like perfect consistency, no gouges, like super hard, well, you're still putting a belt on it. And the belt, like we discussed earlier, has give. It's going to wear unevenly in certain areas. Now, when you use a stone surface grinder, you're only using a portion of the wheel at a time. And so as you use one portion of the wheel and it wears and it gives way to the next portion of the wheel, until you use the entire surface of the wheel, you are maintaining the same flatness and thickness throughout the entire part. The difference with a belt surface grinder is that you are using the entirety of the face of the wheel with the belt on it, of course, every single pass. And so that means that you have the same problem where the belt is wearing at different rates throughout the use as you put in different blanks. So let's say I have a blank that's like this, or I have a blank that's slightly moved up over here, right? Well, that's a problem because the belt is now wearing different amounts in different sections, which means it's now thinner. And because the height and thickness is now different, you're going to have areas that are ground more or less than others, obviously not a flat and parallel part. You will have better parallelism than by doing it by hand because at least you don't have the pressure issue, but you won't have the same flatness as a stone surface grinder. One last word I want to get in is that straightening blades is a very inefficient process. If you can avoid it, you really want to be honest. Some steels, like I said, are less prone to warping than others, and some steels, even if they do warp, are easier to fix than others. Magnecut is probably one of the worst steels, along with AEBL, in terms of warping during heat treatment. Doing it my way is a lot safer and better, I think. If you don't need to temper bend every single blade. Obviously, temper bending, because you have to put one blade in at a time for an hour, it's very time consuming, and so you can skip step one if the warp is very minor and go straight to the carbide hammer. But for the extreme warps, you really don't want to skip the temper bending process because you will probably crack your blade trying to fix it with just the hammer. Once you have all of your parts temper bent and or peened with the carbide hammer, put them all in a box, and I would take this whole box to my local double disc grinding place, which will give me parts that look like this, right, with that circular pattern. And then I would just surface grind all of them, and then I would have perfectly flat and parallel parts. I want to do that. All the straightening before I do areas like the spine. And the reason for that is because when you're grinding your spine, you want everything to already be flat and parallel because you're setting your workpiece on the work rest, flat on the work rest. Now, if your part isn't flat, like for example, let's say that it's not flat and parallel and it's bent a little bit, well, then your spine is also going to be crooked, right? So having a flat and parallel part is sort of the basis for everything else that happens. You really need a flat and parallel part to maintain integrity of your part throughout other processes, even when you're grinding bevels, for example. Like imagine if you're grinding your bevels and your blade is completely warped, right? Well, obviously that's going to be a problem when you're grinding the middle section of the blade because your tip is going to be hitting the belt before the middle section because it's curved inward like that. So and also think about it this way, like let's say you're drawing a center line on your blade to mark the center of where your edge is going to be. Well, if the blade is warped, then your center line isn't gonna go to the center anymore. Like you're not gonna have a centered blade. So flatness and parallelism is fundamental to knife making. You need to have flat and parallel parts before you can do any of the other processes. So it's really important to get right. We all have to deal with warp, and I hope that I explained some of the ways that you can fix that particular problem. I hope that was helpful. I'll catch you guys next time. Peace.